In this video, we're going to talk about the NewtonRaphson solution method in a simple example of a spring and a tension. Here, we have a nonlinear spring, and we subject it to an external force. This external force is a function of some loading parameter, for instance, amplitude of loading, and typically it's written as the amplitude times a loading vector. The spring will deform under external force. Of course, it will extend by a certain amount, let's call it A, and it would exert a reaction force, F internal, which is equal in magnitude but opposite in direction to the F external, in the case of equilibrium. So if we write the equilibrium equation, it would be such a form where the F internal is a function of A, and F external is a known variable, known parameter that we exert on the system as an external force. So as I mentioned, this is a nonlinear spring, so we can no longer write the F external A simply as a spring constant times A. And the external force is a function of a loading parameter. So force usually is a function of time. If not, it's a dead load, then it's a constant. And we assume that this external force is independent of A for the time being. And we want to solve this problem using the NewtonRaphson method. By solving this problem, I mean that we want to find the unknown in the system, which is A. So I will first present the full NewtonRaphson method for a softening spring. So by softening spring, I mean that if I plot the external force versus A for equilibrium, I need the external force to be equal to the internal force. This is a graph of internal force in terms of A, and if the spring is a softening subject to tension, then we can see that the slope of this graph is gradually reducing. So this is also the equilibrium path because the system is only in equilibrium when F external equals to F internal. Let's say I want to apply a certain level of load. What I want to solve is to find the A. So I want to find the coordinates of this intersection in the x-axis. Typically, in numerical simulation, we don't immediately apply the full load straight away. We usually take an incremental approach, which means that I subdivide the full load into several increments. So I load it, let's say, starting from the last equilibrium position or at the position at t0. I increment a little bit the load, and then a little bit further, and then a little bit more, until I reach the final load that I would like to apply to the spring. And I find the solution also in the incremental level. So this is called the increments of a loading step. And I find the first incremental solution, the second one, third one, and finally the fourth one. So when I try to find, let's say, the third incremental solution, I start from the last equilibrium, non-equilibrium position, which is corresponding to AT2, which I already found in the last increment, and F external T2, which is the loading that I have applied in a second increment. Starting from this position, I would like to use the full NewtonRaphson to find the solution for AT3. Again, the known are this point and this load level, and the unknown is AT3. Taken in a very generic graph. In this graph, I start with the previous equilibrium position at which characterized by AT and FT external. And I know that I want to apply the load of the current increment, t plus delta t, for instance. To find this new point, the full NewtonRaphson method would start with finding the residue between the current load level and the previous load level. Then, because I know this point fully, I can calculate its gradient. Divide this residue by this gradient, I can get a correction for the displacement. After this is called the first iteration correction. And then I can find the corresponding internal force at this correction. So there is a new residue. So this is residue after the first iteration. Then this point is fully known. I can calculate the gradient. And now I can use the gradient and divide the first residue after first iteration by this gradient. I can get a new estimate for the incremental solution. So this is the correction. This is the first estimate. And the first estimate plus the correction would equal to the second estimate for the delta A incremental displacement solution. I can repeat the procedure until I reach convergence, which means that this. So basically, this procedure can be summed into such an iteration plot. So all these are called Newton-Raphson iterations. Note that these perform within an increment. To sum up, we first calculate the residue after a certain iteration, then we calculate the tangent, and then we subdivide the residue by the tangent, and we obtain a certain correction. This is a correction, and then we add the correction to the last estimate. We get the new estimate for the incremental solution. This is the full Newton-Raphson method. If you look at this full Newton-Raphson method, it converges very fast. So for instance, in this picture, within 3 iterations, it has already reached the point of intersection. However, we need to calculate the tangent stiffness after each iteration. In a larger problem with more degree of freedoms, this is quite troublesome, and especially that we need to calculate this term, which is the inverse of the tangent stiffness matrix times the residue. This is extremely troublesome because we need to invert the tangent stiffness matrix, and this is a very costly procedure. So people come up with a modified Newton-Raphson, which means that I'm only calculating the tangent stiffness once in the increment. Basically, I'm going to use the first iteration, the beginning, starting tangent stiffness throughout the increment. What it means that it's obviously cheaper because I only calculate the tangent stiffness and it's sort of inverse once, but the drawback is that it takes more iterations to converge. Then people come up with a modified, even cheaper version of modified Newton-Raphson, which is called the initial stiffness method. In the initial stiffness method, the tangent stiffness is only calculated at the first iteration of the first increment, and then used afterwards for subsequent iterations of all the increments. Then obviously, you can see that it's going to take even longer to converge, although it's economically cheaper. So this modified Newton-Raphson is generally not recommended for very nonlinear problems. Then people come up with a variant of Newton-Raphson, which is called quasi-Newton. Here, instead of taking the tangent, what is different is that after the first iteration, we would connect the last known equilibrium position with the current estimate to get sort of a tangent line. And then we use this secant tangent. We use this secant stiffness to calculate our correction. And then we continue this procedure. We form a new secant line, and we calculate our new correction. And eventually, this will converge to the right solution. This quasi-Newton is based on secant stiffness, and is, in terms of performance, it's in between full Newton-Raphson and modified Newton-Raphson. It is very cost-effective way to calculate nonlinear solutions, and it's recommended when you have a very large system equations to be solved. Of course, we can apply the same procedure when we have a hardening behavior instead of softening behavior. In this case, the first estimate would overshoot the actual solution, and then it would through iteration come back to the equilibrium position. I encourage you to try out the drawing of these kind of iteration plots yourself for the hardening behavior. So this, I've already shown you the full Newton-Raphson plot. You can try to draw the same thing for the modified Newton-Raphson and secant Newton-Raphson and see what the graph looks like. In the previous slides, I've only mentioned about external force that is independent of the displacement degree of freedom solution A. In reality, however, there could be cases where the external force to the system is also a function of the solution. That's the case when you have pressure loading, then the pressure would basically follow the deformation of the surface, and then the direction and even the magnitude of your force would change with respect to the solution of the system. So how do we take into account of this effect in the solution of Newton-Raphson? The difference here would be that now the external force is a function of A. We can no longer plot a straight line for each level of loading, so it must be a function of A. In this case, let's say that the external force decreases with respect to increasing of A. And then the rest of the procedure is quite similar. So we do the Newton-Raphson, we calculate the tangent. One thing to note is that the tangent line that is plotted here is no longer the actual representation of the tangent, because when we calculate the residue, which is equals to the external force minus the internal force, and then calculate the tangent would have two contributions. One from the tangent of external force, the other from that of the internal force. Previously, we did not have the contribution from external force. Now we have it, and it's called the force stiffness, or the load stiffness. So now this line here is only representing the contribution from the internal force. So it's not the true representation of the tangent stiffness Ki. And then we do the same to update the displacement correction. So you see that this is not an exact expression of what's happening. A better approach is to directly work with residues, and we can directly form a function called residue function. Now it's a function of A, and the residue is a parameterized function by lambda, which is the loading parameter. Now we can plot the line of residue after each loading increment. So we start with the first increment. We have the first residue function, and we gradually, through iterations, find our first solution for the first loading increment. And then we increase the load, we suddenly have a nonlinear, non-zero residue, and then through iteration, we find our solution for after the second increment. And then this repeats until we reach our final load level. For each of these increments, we can perform NewtonRaphson. So here we directly work with the residues. We find the first residue, we calculate tangent. Now this is the true representation of the tangent. And then we update the residue, and then we update also the tangent. This is the case for full NewtonRaphson until we find the solution. And again, this is the procedure. We calculate the residue. Note that it's directly working with the residue instead of writing as f external minus f internal. And then we calculate tangent, and then we update the incremental solution. So this is a very general procedure which works for both follower load and non-follower load. Of course, we can also plot the same thing for modified NewtonRaphson or the secant tangent. This would be the plot for the quasi-NewtonRaphson. I've talked always about convergence, about finding the converged solution, but never actually mentioned about when do we define it as converged. The trivial answer is when the residue is zero. However, numerically speaking, we can not afford to look for absolute zero in our solution. Otherwise, we will never be able to converge. So we need to work with some tolerance. One of the most straightforward tolerance is based on force residue, the magnitude of force residue. So basically, if after a certain level of iteration, at ith iteration, for instance, the magnitude of our residue is smaller than the initial residue, considerably smaller, let's say it's only less than 0.1% of the initial residue magnitude, then we can say that it's converged. This is one type of criteria. Usually, people also look at a second criteria based on displacement, because there could be cases, for instance, in the creep problem, where the force has converged long ago in the beginning, but the displacement is taking time to stabilize. Then we need to look at both the force convergence and the displacement convergence. And one type of this convergence criteria based on displacement would be to look at the displacement correction with respect to the initial estimate of the incremental displacement. And a third convergence criteria is based on energy, which is basically the product of the residue times the displacement correction. And here, if this sort of correction energy is small enough compared to our initial energy, then we can consider it as converged. Now let's look on this graph, what especially this energy criteria, what these terms mean. Now look at the first term. This is the R0 times A1. So A1 is our first, delta A1 is our first incremental estimate. So this is basically represented by this rectangle. And then let's say I on the left side of this inequality, let's say I equals to 1. Then the left term is basically represented by the light green rectangle in this graph. And if we increase the I, we are finding a smaller and smaller rectangle until the area of the rectangle is considerably smaller than the initial big rectangle. Then we can say that it's converged. In practice, it's recommended to use a combination of these different failure criteria, especially different convergence criteria, especially to combine the force residue with a check on displacement. So in summary, I have covered a full Newton-Raphson, and this is the fastest method in terms of convergence, but it's very costly because we need to calculate the tangent stiffness after each iteration. Then I've mentioned about the modified Newton-Raphson. It's cheap because we only calculate the tangent stiffness once per increment or even once per analysis, but it's very slow in terms of convergence, so it's not recommended. And then we have a quasi-Newton, which is somewhere in between full Newton and modified Newton. It can be very cost-effective. Sometimes people even further modify the quasi-Newton such that the secant tangent stiffness is not updated after every iteration, but only after several iterations. So again, it's an even cheaper version of quasi-Newton. It's efficient. It's recommended when a large system equations need to be solved. So in summary, either use full Newton for smaller problems or use quasi-Newton. Don't go for modified Newton. All right, in the next next video, I'll talk about some common convergence issues.